All right, guys, 5.4 is over log functions, and I think you'll notice that when I sent you the PDF, I gave you this great big long table of all the different log rules. Some of the things are not necessarily features that will apply right now, but we will apply them later. So if I have an exponential function, then the inverse of that exponential function is a log function. So this one has an asymptote as x goes to negative infinity at y equals 0. So as x approaches negative infinity, y approaches 0. So we're going to flip that here. As y approaches negative infinity, x approaches 0. There's that feature. And then 0, 1 becomes 1, 0. And then they're going to reflect over the line y equals x. Oop. I'm going to just do that. Sorry, kind of passed through my limit there. And this is the inverse of f of x. Okay. So the domain here for f of x is from negative infinity to positive infinity, so all reals. So the domain here becomes the range here, all real. The range is from 0, but not including 0, up to positive infinity. Whoop. I used old notation. There we go. And then the domain is going to be what the range was here. So 0, positive infinity. There we go. So let's just think back to our basic log ideas. The log base b of x equals question mark asks b raised to what is x? Okay. To what? Question mark. So if I said log base 3 of 9, I could say that 3 to the x equals 9. So those two things are directly related. I could say that log base x of 2 equals 7. And so x to the 7th equals 2. And then if I wanted to solve that, I could take the 7th root of both sides, but that's not really where we're going. We're just looking at translating back and forth. Let's just take some time to do some simplifying. So let's say log base 10 of x. Okay, this is called our common log because it's a base 10. And then ln of x is called our natural log. And this could also be written as log base e of x. Let's look through at some of these rules real quick. And then we're going to do a couple application problems where we just solve some things. So as long as two things have the same base, they could be written as the product. Okay, log base b of x minus log base b of y can be written as the quotient, so long as they both have the same base. Log base b of x to the y becomes the multiplier. Log base b of c is equal to 1 over log base c of b. Okay. Maybe we'll look at that one real quick. So let's say I have log base 3 of 9, which we know equals 2. could be written as 1 over log base 9 of 3. So 9 to the what is 3, 9 to the 1/2 is 3. So 1 over 1/2. Well, are those two values equal? Yes. So we can see that the two things are the same. This is the change of base formula. We will use this a lot. The reason we need to use this a lot is that, think back up here with the product rule or the quotient rule. If these don't have the same base, I can't do anything with them. So I may have to do some change of base trickery in order to make these things work. So, if I need to solve an equation or something, I need to put them in the same base. Derivative and integral, we won't work on those for quite a while. The logarithm of a negative number. So log base b of x is undefined if x is less than 0. Think about the graph. Okay, x cannot be a negative number. It can also not be 0 because we have an asymptote at 0. As x approaches 0 from the positive side, so what does that mean? That means that as I take my finger and I run it down towards x equals 0, I'm going to get closer and closer and closer and closer to 0, but I'm coming at it from the positive side. So log base b of x for this function, the output of that is getting closer and closer and closer to negative infinity. So as this gets closer to 0 from the positive side, the output gets more and more negative, closer to negative infinity. Okay. Log base b of 1 is 0 because anything raised to the 0 is 1, and anything raised to itself is b. So a couple of important rules there. The logarithm of infinity. Ooh, weird. So think about it this way again, come back to our graph. As I input a value that's larger and larger and larger, I'm outputting a value that's larger and larger and larger. So that as x approaches infinity, the output approaches infinity. All right. Let's look at a couple different values. Okay, so let's simplify one. Simplify log base 3 of m plus log base 3 of n, subtract log base 3 of p, and let's go ahead and make the log base 3 of p. Let's multiply that by 2. So there's my initial expression. So I'm going to see if I can write it in terms of a single term. So using our product rule, this can be written as log base 3 of m times n minus 2 log base 3 of p. Now I can put these two together, but I'm going to have to take this 2 here and bring it back up to be the exponent on p so that I can make this work. So this is going to become log base 3 of mn over p squared. So that 2 came back up here. This part of this whole thing could be written as log base 3 of p squared. So those two values are equivalent. So if I'm going to write this as a single term, that's how you can write it. Okay. All right.